Good afternoon, everyone. My name is Marco Giulio, and I'm from University of Naples. This is the title of my presentation, Experimental Behavior of 3D Printed Concrete Wall with Fixed Base Anchorage subject to plain cyclic loads. This is my presentation outline. We will see an introduction, materials and methods used, test setup and instrumentation, experimental results, and conclusions. The main goals of this study is to analyze the structural behavior of a 3D printed concrete wall under in-plane cyclic loads, study the crack propagation mechanism and failure modes, and provide insight for improving cyclic design of a 3D printed concrete elements. This is the material properties at the material scale of the material used during the test. In particular, we can see in this table the properties along the double direction orthogonal to layers, and we can see the compressive strain value is almost 45 megapascal, and flexural strength is almost 8 megapascal. In this slide, we can see the printing process, in particular how we have fixed the base with the wall. We have used this prefabricated element. This element is composed by two steel prefabricated elements, HAB anchor bolts and ACC cone shoe. The HAB anchor bolts is embedded in the foundation, and the ACC cone shoe is embedded in the wall. The layer 8 is 10 millimeters. The total number of layers is 210, and the interlayer time recording is 1.5 minutes. In addition, we can see the cross-sectional area, and in particular the maximum dimension of the wall along x and y-axis are 1.3 meters and 0.55 meters. And this table, we can see the geometrical properties, the area and the value of inertia along y and x-axis. The tests are developed in the Department of Structure for Engineering and Architecture of Naples. And we can see the photo of the test setup, and on the right side a sketch of test setup with the instrumentation used. In particular, the tests are developed in the displacement control, and the horizontal load is applied by these horizontal actuators. And to apply the axial load, we have used two jacks on the tops and two orthogonal beams. The value of the axial load applied is 58 kilonewton to simulate an overhead structure. This is the main output of this test, and it is expressed in terms of lateral force with letter B versus top displacement with letter delta top in millimeters. We can see in gray a cyclic curve, and in black line the envelope data or backbone curve. The behavior is really similar in push and in the pull stage, and we can see before the onset cracking point an elastic state, and after the onset cracking point we can see a softening state. The value of the maximum value of the lateral force recorded is 66.25 kilonewton, and the maximum value of the value of the top displacement in the elastic state in the onset cracking point is almost 0.45 millimeters. In addition, we can see the crack pattern. The crack initially occurs in the external part of the wall, and after the propagation, they are propagated in the middle of the wall. But if we want to describe much better the damage propagation, we can plot the vertical opening versus slippage on this graph. In particular, vertical opening on y-axis is the displacement recorded by the RVDT called the CTDOD across the cracks, and this represents the bending failure mode. Along the x-axis, we have plotted the slippage and the displacement, the relative displacement, recorded by 2 LVDT, this 2 minus display 1. Now, if we catch the onset cracking point in terms of this displacement, vertical opening and slippage, we can see that before the onset cracking point we stay in elastic state and the slippage and vertical opening are similar. But after the onset cracking point, we can see the vertical opening are predominant, and the bending failure mode is really predominant. So, but if we want to give an analytical interpretation and comparison with the classical measuring formulas according to Eurocode 6, we can see the neutral axis in push stage or pull stage is really similar, and we can plot the stress diagram, in particular the compression stress and the tension stress. Now we know the classical failure modes in masonry. They are 3. In particular, flexural compression, diagonal cracking, and shear sliding. If we apply the formula for masonry according to Eurocode 6, we can note that the value of diagonal cracking is really similar. The value of lateral force calculated by analytical formula of diagonal cracking is really similar to the value of the experimental test. But we have only one difference. The difference is in the crack direction, because the crack direction in our case is influenced by the orientation of the layer and by the geometry. In conclusion, we can assert that the 3D printed wall show an high stiffness with a peak shear force of 66.25 kN and second stiffness average of almost 115 kN/mm. With 45 megapascal of compressive strength, the 3D printed concrete is much stronger than traditional masonry. Because if we compare the value of the traditional masonry in the table of Eurocode 6, we can see a value in a range of 1 and 10 megapascal. And this is the reason why reducing flexural compression failure mode risk. About the failure mechanism, the initial bending cracks at weak layers cause failure onset, similar to diagonal crack in masonry, but only in analytic terms, because the direction of the cracks is influenced by the orientation of the layer, by the geometries. For this reason, for future focus, large-scale testing is crucial to assess the material's mechanical properties from material to structural scale, considering scale effects and printing process. Thank you for your attention.
So, thank you, Marco, for your nice presentation. Very interesting experimental investigations.